Okay, all right. My name is Brijesh Singh. I work at AMD. I work in Linux OS group. Recently, I've been working on this memory encryption technology. This technology is not available in current product, but it will be available in future products. And today, I'm here to talk about what this technology is. And since this is memory encryption, there are some key management involved. We'll talk about a little bit about what the key management means, and then some integration efforts, what it will take to integrate it in the Zen hypervisor. So first technology. So the main motivation behind doing this memory encryption is what we are seeing, like, okay, there are a bunch of encryption algorithms available for the disk, but the data available in the DRAM is just still plain text. So anybody can snoop in the DRAM and can look at all the contents. So one of the job which hypervisor does pretty well is tries to isolate the co-resident VM in a system. And some of those things is done by, if you're using hardware-assisted virtualization like AMD virtualization technology, there is also logical isolation using the page table, VM intercepts, and all those things. But things could still break down. And so like one of these CVs where one of the guests could exploit vulnerability in hypervisor and can get into another guest region. And another thing which we have been constantly getting the feedback from customer is that some of the cloud users do not have full faith on the cloud provider. And cloud provider also thinks running all the data as the liability, because hypervisor is the one who is isolating all these co-resident VM. So hypervisor has a full access to the guest memory. So it has all access of the guest memory secrets and stuff. And probably it's not idle for both cloud provider as well as the cloud user. And so this technology is going to help answer some of those questions. So there is two technology will be available as a part of memory encryption. One is called SME, Secure Encrypted Memory. And then another is called SEV, Secure Encrypted Virtualization. So SME is the one which is going to help us in the physical attack surfaces. For example, probing the physical DRAM. The technology will help us to help us on that attack. Or if somebody installs hardware to probe the DRAM interfaces, and of course nowadays we get the NVDIMMs. All the data is available in the NVDIMM. Somebody can steal the NVDIMM, and then SEV can actually help us the user attack surfaces. For example, administrator can scrap the guest memory because hypervisor has full access to the guest memory, or somebody can inject some code directly in the guest memory, and the SEV will help in those. Or if there is one guest can somehow exploit the vulnerability of hypervisor and steal the data of another guest. So SEV is going to help in one of those attacks. So the way this technology works is there is a memory encryption, AES memory encryption engine integrated directly inside the memory controller. And it performs inline encryption, 128-bit AES inline encryption and decryption as and when the data leaves and enters in the DRAM. There is very minimal performance impact, like when we are doing encryption and decryption. There will be impact, but it's very minimal. But the good part is there is no application changes required. Most of the changes will be confined inside the operating system or inside the hypervisor. And the keys used for encrypting the memory is actually only known to the AMD secure processor. And AMD secure processor is totally isolated from x86. x86 will never be able to see any of those keys in plain memory. So that's what this diagram shows, that the memory encryption engine is built directly in the memory controller. So if you have multiple controllers, each controllers will have their own memory encryption engines to do the encryption and decryptions. So first one is we'll talk about the SME, Secure Memory Encrypted. SME helps in the physical attacks. So the idea of the SME is actually very powerful and very simple technology. It scales pretty well from high workload, like server type of workload, to the embedded workload, even very small workload. The idea is at the boot time, system would generate a random key. So this random key is again generated by the hardware random number generator. And the key is stored in the secure processor. That's PSP is what we call platform secure processor. It's stored in the PSP. And then all the memory gets encrypted using that random key. And the operating system or hypervisor can choose which page can be encrypted through the page table. So there is a bit in the page table. If you set that bit, then memory gets encrypted and decrypted as and when it gets read or write. And again, the hardware devices can still do the DMA using encryption and decryption methods. Only catch over here is the C, we call it C bit, the encryption bit, we call it a C bit. The location of the C bit is actually determined using one of the CPU ID call. You do the CPU ID call, it tells you where the position of the C bit is, where the C bit should be set. And what we are seeing is the C bit position is actually bit number 47. So if you have legacy devices doing DMA 32-bit, then we probably have to consider using bounce back buffer or use IMMU or something like that, by which we can access to that bit 47. But if your DMA is done by using up to 48 bits, then we are just fine. We don't have any problem over there. So a little bit more detail about programming aspect of the SME. Very simple, call the CPU ID function, get the information, whether the memory encryption is supported on the particular hardware. And if it is supported, then again, do another MSR, sysconfig MSR, set the memory encryption mode. And then in your operating system page table, set the C bit. And if the C bit is set, then memory gets encrypted and decrypted as and when it's read. So that's what this diagram is actually basically showing, is that if the C bit is set in the PT, then any of the memory read from the CPU will always go through the encryption and decryption engine. And again, the location of the C bit is determined by calling the CPU ID. I think it's the same CPU ID, just different registers. And one more thing to note here is that this C bit is accessible only when we are when the paging is enabled, basically when we are in PAE mode. So if the code is in real mode, the C bit is not accessible. So programming point of view, I think, okay, probably operating systems, it can enable the paging and it can go and set the C bit. But when we are in the BIOS, the C bit is not accessible. So the BIOS is still coming up in the plain memory. So I think I was looking at Zen kernel and trying to understand the booting sequence a little bit, and to identify the place where we might consider enabling the encryption. I think one place which I could see it, when Zen boots up, it relocates itself from low memory to high memory. And when the relocation is happened, probably that's the place where we can enable the encryption. And from there onwards, the entire Zen kernel itself will start getting encrypted. But I think, and then another, yeah, that's one piece. And then I think UEFI we also need to consider, because if the system is booted through the UEFI, then UEFI already loads the Zen in the high memory. So there is in the documentation, actually our APM is pretty well described that how you can do the inline encryption when you have these type of situations. And so this is about the SME. In SME, so basically there's one key, and that key is randomly generated at the boot time, used for encryption and decryption. And next one is SEV. So SEV is tightly integrated with the AMD virtualization technology. And what this gives you is each VMs can have their own keys. So for example, what I'm trying to show over here is like Zen hypervisor, and one of the PV guests is using this key, which is we call a root key, because Zen hypervisor is going to use the key 0. And then one of the PV guests can use his own key. Another HVM guest can come and use his own key. And you can have another guest which is actually not using any of the key. It could be unsecure guest. And so idea behind this is hypervisor is isolating these VMs, and SEV adds extra isolation, a cryptographical isolation from each other. So if somehow one of the guests breaks in to the hypervisor, if he tries to access another guest memory, he will not be able to do that, because that guest memory is encrypted through different keys. Yeah.
So if we use PVW, they share all the same keys, right?
Yeah. Yeah, yes, yeah. If you're a true PV guest, you are not using the VM runs or SVM technology, then you will not be able to choose unique key. But still, at least you will be protected through physical attacks. So here's architecture, software architecture on how this is going to look like. So so in case of SEV, since there is a key management involved, it means there has to be some communication between the guest owner and the cloud provider. So I think the step number one, I would think, is the guest owner asks the hypervisor, please launch SEV guest. So hypervisor is probably going to respond back to the guest saying, hey, OK, give me your public Diffie-Hellman key so that I can launch a guest. So there will be some communication between the hypervisor and guest owner. Once he gets all the keys and stuff, then hypervisor will call this SEV driver, very lightweighted driver. So SEV driver is the one which is going to talk to the AMD secure processor. So he will send some commands to the secure processor, and secure processor is the one who will go and program the keys in the memory. And from there onwards, it will get encrypted and decrypted. All the access of that particular guest goes encrypted and decrypted. So the idea over here is key is never visible to the x86. Only thing which what x86 is actually able to see is some of those MMIO registers exposed by the secure processor. And so slightly more detail about the CV. So the way key are managed is actually through the ACIDs. So in the VMCB, you have the ACIDs, which we tag. The ACID gets tagged for all the data inside the SEV, inside the CPU, actually. But when the data leaps, then it is always going to get encrypted. When it goes to the RAM, it's always going to get encrypted and decrypted. So everything is tagged through the ACID. So what you can think of is hypervisor. The ACID is nothing but the index to the key. So let's say one guest gets the ACID 1. It means he's actually pointing to the key number 1. If he's getting ACID number 2, then he's pointing to key number 2 or something like that. And so there is some limited number of the SEV guests you can launch. And again, you can call the CPU ID function to get the maximum range of the ACID supported. And so when you're allocating a SEV guest, pick up the ACID from that particular range. You cannot just pick up any arbitrary ACIDs. So I think I know I have seen that, like in KVM hypervisor, they increment the ACID as and when a new request comes for the VM run. That is definitely not going to work because ACID has to be picked up from the range given by the CPU ID. And if Zen is doing that similar thing, then we probably need to do that. So I think, yeah, in KVM, I have already submitted a patch where I reserved certain ACIDs, and SEV guest will pick the ACID from the range given by the CPU ID. And another thing is, in case of the SEV guest, there is this concept of the private and shared page. So private page is basically the page which has the C-bit enabled. Shared page, basically unencrypted, means C-bit is disabled. And so in case of SEV, all the code is considered as a private. And guest page table itself is considered as a private, yes. So the guest has to set these bits itself, otherwise it won't work? So yes, so the guest has to set his own page table. So when a guest is setting the page tables and whatnot, he has to set the bit. Okay, so if this is enabled, then a shared page will sort of implicitly be marked no execute? So the idea is the shared page is nothing but the data, whatever you can copy in and out. I know, but I'm trying to think of it as an attack where it can. If the guest messes up. Yeah, absolutely. Yes, absolutely right. Yeah. If guest purposely is saying, oh, this is shared page, means he is giving right that whatever I can put in that code. But the hypervisor set like a shared page, write its own code and then jump into the context. Can you execute on a shared page or not? I don't think they will allow you to execute on the shared page. Okay. Yeah, definitely. They would not allow you to execute on the shared page. On the destination side, do we need to I'll go through that. I'll go through that. So yeah, another thing here is in case of SME, if you remember, I told like the C bits get set only when the paging is enabled. But in case of SEV, it's slightly different. Encryption is enabled from time 0, means when the guest is calling the first VM run, encryption is already enabled. It means the BIOS is actually always in encrypted mode. So, and all the DMA operation definitely has to be done on the shared pages. Yeah. So this slide talks a little bit about the CV and SME interaction. I think it summarizes pretty well. So if we are on the host, which is ACID 0, inside the hypervisor, then C bit of the hypervisor space table determines what keys to use. If the C bit is set, it means it is going to use the host key. In case of the guest, if it is non-SEV guest, the nested page table is which going to determine whether the page is encrypted or not, and also it will use the host key, which is key 0. But if it is SEV guest, then guest space table determines which key to use. So basically, yeah, in case of SEV, the bottom line is guest tells what he wants to share and what he doesn't want to share. So a little bit more about the key management, because there's a lot of the key management is involved basically in case of SEV. And so one of the things which in the SEV architecture slide I shown is the PSP firmware, SEV driver talking to the PSP firmware. So what this firmware is the one which actually executes some of the commands which we send for the encryption and stuff. So firmware, our platform security processor, exposes 3 MMIO registers to us. First register takes the command ID and also response, and then other 2 registers are just the DRAM command buffer. So for example, if guest owner says, okay, I want to program this particular key, then hypervisor will get the request. Hypervisor will write the command ID, which is like one of the command we'll call launch start. And then all the key and stuff is actually given in a command buffer. So he may allocate a 64-bit DRAM address, put the data over there. SEV firmware will fetch the data, perform whatever the requested operation has been, and program the key, and then return the response back with 1 bit whether the command was successful or not. And this entire firmware is actually designed with VM lifecycle in mind, basically. Bootstrapping is starting from ground 0, launching the guest, and also the migration pieces has been taken care. So all those things has been pretty well taken care inside the firmware. And I think that's where, since this is yet not available, we definitely want to get more feedback on the firmware side. What are the things can be improved on the firmware? And so, for example, when you're migrating data from one place to another place, probably during migration, you want to encrypt the data using your transport key. So you send a command saying, okay, from guest memory this to this, encrypt it using my transport key. So he gets encrypted using his transport key. The data is sent over. On the other side, there is a receive command. Hypervisor will run the receive command, and he will start unwrapping through his, again, the transport key and re-encrypt it back to the original key on that side. And over here, on the remote side, you can pick up whatever ACID you have decided. ACID is not dictated by the commands. It's just a random pool which is available to you. You can pick up whatever ACID you want. But the thing is, you will pick up the ACID at the basically bootstrap time before the guest is running. You pick up that ACID. And when you're creating the guest, there is this also concept about the guest policies. So you can set the policy. What are the things you can do on that particular guest? For example, one of the policy could be the debug, whether the debug is allowed or not, because now all the guest memory is encrypted. So maybe if you are in early boot sequence and your system is crashing, you will not be able to inspect the memory cleanly. So if the debug policy is set, then the debugging will be allowed. And similarly, I think there's one of the policies whether the migration is allowed or not, whether you can migrate the SEV guest from another non-SEV guest. And also there is a bunch of other parameters, for example, version checks and whatnot. all those things is given over here. So here's a bunch of the commands which is the SEV firmware actually accepts and listens. So first setup command is a launch. We call it launch API. Like launch start command. So launch start command is one which takes the so launch start commands and stuff, they are used before guest is running. So it's just preparation of the guest. So for example, launch start, one of the argument in the launch start would be is the guest owner's private Diffie-Hellman key and his policies and stuff. So you get that information, you send it to the SEV firmware, he goes and loads the key in the memory, and now a hypervisor will probably start copying the kernel, initial RAM disk stuff in the guest memory, and then you call the launch update, which takes, okay, where you have copied the data, I'll update it, encrypt it on fly, and then finally you call this launch finish command, which does the measurement of all the copy it has done and send the measurement. Now you can send that measurement back to the guest owner. He can authenticate whether the guest was really successfully launched over there. And the same thing in case of migration. When we are about to migrate, the send start command will be called. Send start command is going to accept, I think it's a bunch of certificates. Like one of the certificate is going to be remote destinations, all this information, and some transport keys and all those things. And then send update command is the one which takes the region of the guest memory and goes and re-encrypts it. And then send finish is again going to generate the measurement, which receive finish can validate whether the measurement was good or not. And of course, to make things a little bit easier, there is also a debug APIs. So one of the debug APIs is like debug decrypt and debug encrypt. So debug decrypt is going to decrypt guest region, whereas encrypt is opposite. It can be used to inject certain code. For example, when you are debugging this SEV encrypted guest, probably I can think of one reason why I need the debug encrypt is breakpoints. If I want to set the breakpoint through outside GDB, then probably I will need debug encrypts and those commands. And then last one is the certificate management APIs or commands. Basically, many of these are very well explained in the SEV management APIs, and yeah, I think a lot of these are pretty explained. So yeah, in next section, I want to talk a little bit about the integration, what it will take to integrate in Zen hypervisor. And I'm pretty sure as we start implementing it more and more, we'll find more and more issues. And so recently, we have submitted the patch for SME in the Linux kernel. I think it was submitted in April of this year, and then V2 went this week. And I have also submitted the SEV patches in the kernel, and I'm working on getting something out to the Zen also, Zen community, and get some feedbacks. So one of the things which we need to work quite a lot in the SEV side is the integrating this guest management APIs. So I think first thing I can think of course, we have to develop some SEV drivers for Zen. And basically all these things, I'm pretty sure will require some changes in upper layer stack, because there is some communication goes between the guest owner and the hypervisor. So for example, like wrapping, unwrapping the keys and stuff, and talking to the AMD secure processor and getting the measurement back to the guest, and so the guest can say thumbs up, now I can hand over my disk encryption keys and whatnot. So there will be some amount of work in the key management integration. And next is this ACID management, like we talked about. ACIDs, we have to pick up the ACIDs from the SEV guest range. And so there will be one good catch over here is that I think most of time when a new vCPU picks up another ACIDs, a new ACIDs, but in case of SEV guest, all the vCPUs should share the same ACIDs. And since they are sharing the same ACIDs, if the vCPU was ever scheduled on a different physical CPU, then that's fine. But if other CPU was scheduled over there, then we have to do TLV flush on the guest. So those kind of things is what we have to take care inside the ACID management. And of course, non-SEV guests are free to use those assets, but they will just eat up the resources. And yeah, and then similarly, the debug has support. And so I don't know much about how Zen debug is done, but I know in a QEMU, for example, you can do that XP command to dump the memory, or you can use a GDB server. And these debug APIs can very seamlessly be integrated inside the QEMU to read and write the guest memory. And so that we still have those old backward compatibility. And okay, so just to summarize everything, what AMD has been doing is AMD is developing definitely SEV firmware that will be part of AGISA, and it is signed by AMD, and it is a closed source. But then whatever the changes we are making inside the Zen hypervisor or guest kernel, all those things is going to be open source, and it will be available for available as RFC for further comments. And like I told, we have already submitted RFCs for SEV and SEMI in the Linux kernel mailing list. That's all I have. I think one more slide I wanted to show you guys. So this gives some comparison. I haven't talked about this something called transparent SME, which we are working on. The transparent SME doesn't require any operating system changes and whatnot, so I thought there was no use of mentioning in the Zen Summit. So what SME basically says is protects against the physical attack. Same is the transparent SME, but SEV is the one which protects against some of the user attacks. And so in case of SME, there is only one key used for encrypting the entire DRAM. Same is the transparent SME. Whereas in case of SEV, one key per VM you can get. And again, the encryption is, in case of SME, encryption is enabled by the page table, NAD page table. Only difference is in transparent SME, encryption is enabled by the BIOS. So once you enable it, you forget it. And then in case of SEV, guest page table is the one who controls the encryption. And DMA, in case of SME, any pages can be done. And same for the TSME. But in case of SEV, the DMA will be done only on the shared pages. And so SME and TSME, they don't need any of the SEV drivers and stuff. Whereas in case of SEV, we probably need a driver. And here's the software impacts about these. Okay. I think any questions? I will be. Yeah.
In January, an agency of the US government issued some recommendations over selection of cryptographic protocols. And your use of AES 128
That's right.
Caught my eye, as that one is now specifically no longer recommended for confidentiality. So I was wondering whether there's any flexibility on the selection of the encryption algorithm being baked into this platform, or whether you're fully wedded to that choice.
So what I know, looking at the documents and stuff, no, it's not possible that you can pick and choose. It's hardwired as a 128-bit encryption algorithm. But I'm sure probably in future, it's first revision of the technology. I'm pretty sure in future probably they'll look into those things.
Thanks.
I have another question. I'm not sure if you know the answer on that, but the way the encryption is done, is there a randomization vector included for every line? Because I assume it encrypts with 128 AES 128 bits every line of the memory, right? So is there a randomization vector included somewhere? Because otherwise, all my zeros will look the exact same way. It is trivial for me to scan the memory, find the zeros, and find the key.
I don't know the
answer. In other words, without randomization, right? I can.
So I think what you're asking is, are you using ECB? Are you using CDC? Are you using what are you using basically?
I think that I already have my security architect over here, and I can ask him.
You know, it's more than that, right? Because if you do every line, right, and then you need a random number per line. If you don't have a random number per line, you end up scanning the memory, you know where the code is, right? So if I run Linux or whatever as a guest, I know what the code is loaded there with very high probability. I know exactly what the ciphertext is, what the clear text is.
No. So there is a tweak. There is address tweak. So you cannot. So for example, you take a ciphertext, and if you copy that ciphertext somewhere else, you will get scrambled data. There is address tweak already implemented over there.
But I'll get the ciphertext, right, if I prop the memory.
Yeah,
I will read the ciphertext, and I know what is the clear text. Therefore, I deduce the key. That's why.
But how you will derive the key?
Anyway, it's.
Okay. But I think, I mean, yeah, my security architect over here, I can pretty much ask that question to him.
Can you please compare and contrast this with Intel's SGX?
I'm here to talk about
or like,
this. I'm not here to talk about the products.
Oh, okay.
And
okay.
Different, ours are more expensive.
Yeah, okay. Well, it seems like you could implement one with the other, right? You can implement one with the other.
I mean, SGX is targeting a completely different market. Yeah.
But could you do SGX in the hyper?
For example, specific applications.
Yeah.
We look at applications, so we don't need a modification to the guest kernel, right? But you need to modify, extend your application to take advantage of SGX.
But they're
no, we are just changing.
It's the hosting device, right? Like SGX, you have to call into. There's no, can't do an interrupt into an SGX code and stuff. It's different. It's the application has a, like, call it a secure volume that it can call into.
And then in our case, for example, VMX, all registers are clear, so it doesn't expose any secret in the unclear stuff. I think that you guys.
Yeah, that's right. The CPU state registers are still in the clear memory.
Yeah, so it's like a container. It's like a container rather than this is kind of transparent memory. It's yeah. So
lower level.
There's two different markets.
Yeah.
Now is the only link-free solution.
Yes.
So on the subject of protecting keys and making sure that blocks can't be used to derive the key, this sounds like it should be like IEEE 1619 that we use on storage, where you basically encrypt the block offset as part of the cipher. So that way you know if a page has been maliciously copied from one place to another, because you also get an authentication check. The thing that concerns me more is actually the DMA requirement here. Have you got any plans to, for example, if someone's using shared page tables between the IOMMU and the CPU, why can't we do DMA directly to encrypted pages? Because with this today, as soon as I do GPU pass-through or SRIOV, I can't use encryption at all, right?
That's absolutely right. Yeah, and yeah, that's absolutely right. And like I was saying, this is the first iteration. I'm sure in the future, they are starting considering all those aspects.
Any other questions?
Andy, you had any question?
And,
So presumably with this, anytime the VM would trap out the hypervisor for emulation or something like that, we'd be stuck because we can't read the instruction stream.
So yeah, there are certain instructions. For example, if the VM exit happened because we are not able to emulate the instruction, then those instruction bytes will still be decrypted and present in the VMCV saved area as a plain text. So we should still be able to do certain opcode reads.
What about trapping for an NPT fault?
So
which is the most common reason for trapping for emulation in Zen.
Right. So I think one of the, so we are basically trying to find out what's the physical address and stuff for that. And the thing is, when the VM exit happens, there is this exit info 2 register, which actually can give you the guest physical addresses and stuff. So you don't need to do all those page walks. We have seen that KBM was doing it, and we fixed it.
Also in Zen, we use that information if it's available.
So,
But it's very common, emulation going to QEMU, for example, where it traps because of missing page fault, and we have to emulate the full instruction.
So yeah, I think like I know there is one or two instructions which they don't support in SEVs, like for example rep moves, string IO instructions. They always get trapped, so we have to unroll those instructions. So there are certain set of instructions which are still available in the VMCB saved area, which is detailed is present in the APM, like what instructions are still available. But not all instructions, because most of time instructions can be handled in the VM run area. So there are still some instructions which, so yeah, that's why I think the first iteration has given, there are some information can still be leaked, like CPU register, some of those, for example, MMIO, right? You're emulating the MMIOs. When we see MMIO, then VM exit is going to give us the information that trap has happened because of the MMIO, and the save area will have the plain instructions. So the instructions over there will be decrypted back.
That's fine for the instruction stream, but what if it's got a memory operand?
Yeah, so I think that is, I don't know the answer for that.
I presume the answer is it doesn't work. And it's fine with a whole lot of technology like this. We do have to accept that there may be limitations on what you can do.
Yeah.
For guest.
Yeah. I know. Yeah.
We know what these limitations are.
Yeah. One instruction I know for sure doesn't work well is the rep. So if you are doing rep ins, the rep ins instruction is not going to work because it needs 2 memory operands, so they cannot decrypt both the data. So that's why one of our patches basically unrolls the reps, doing a single ins and outs. So that for sure I know. Other instructions, I don't know which one, but I haven't came across any yet. But I think what I can do is we can grab David Kaplan. He's our security architect. He's here. He can tell us if there is any other instruction which we need to be aware of.
Okay, thank you.
Okay.
I was just going to ask what I don't think you answered what is the authentication, if any, or there's not.
Authentication, like.
I mean, to follow up your question, what is there any authentication that of the memory that it has not been, that the encrypted bytes have not been tampered with?
So only authentication I know is at the boot time. At the basically boot time, they do the measurement. When you call the launch finish, it does some measurements of all the memory copied into the guest memory space, and that measurement is what you actually send it to the guest owner to authenticate whether he authenticates whether he's really talking to the SEV guest, and that's when probably you want to hand over your disk encryption keys and whatnot. This makes sense.
So I meant more of like as each page is decrypted that somebody hasn't DMA'd encrypted bytes that happen to decrypt into other valid instructions.
But okay, so if the encryption bit is set, it means it's already getting encrypted and decrypted. So I'm not sure why the authentication need to come in the place over there. It's in case of SEV you're talking about, in case of SEV or SME?
I think the question he's getting more towards is a hostile attack from the outside writing into memory, disrupting it, and then you not knowing, how do you know if it's still valid?
Guys, it sounds to me that this is maybe a good topic for one of these sessions in another room. We have like 17 more minutes for break, and then and a coffee will go and stuff otherwise, right?
Okay.
But, you know, like there's the other room, so you can just afterwards just sit together and sorry for cutting you off.
Okay, thank you.